The main ideas for chapter 9.2 and 9.3 are that one nth order ODE can be converted into a system of n first order ODEs, and that when you do this, you can write things in matrix form and then use all the stuff that we learned about linear algebra, which is actually why we spent all that time learning about linear algebra in the first place. So let's look at just an example. So suppose we've got a second order ODE like y double prime plus 4e to the t y prime minus 9t squared y equals 7t. Okay, so this guy is non-homogeneous. It's linear, but it does not have constant coefficients because the coefficients depend on the variable t. Okay, so the technique for converting this into a system is really simple. We just look at the unknown function y, and we replace it with a new unknown function called x1, and then we replace y prime with x2, and so on and so forth. Now, for this one, since it's just a second order equation, I only need to have two variables here, since, okay, so this one is second order. So that implies that I only need two variables here. If it were, you know, like a third order equation, then I'd need an x3 and so on and so forth. Now, from this, let's see what happens if we take derivatives. So if we do ddt of this, then we see x1 prime is equal to y prime, and x2 prime is equal to y double prime. So now I've got everything that I need to substitute into this equation. I've got a y double prime, a y prime, and a y. And you notice also that x1 prime is y prime, which is also the same thing as x2, because of that's what we chose x2 to be back in the first place. So let's see. So now when I look at my equation, I can replace the y double prime term with an x2 prime term, and then what I have here, I've got 4e to the t, and then y prime I can replace with, well, I can take my pick of x2 or x1 prime, but x2 is going to make life simpler because it doesn't have the derivative. So I'll go with that one, and then minus 9t squared, and then y was x1, and then this is 7t, right? Okay, so let me just make a note. Easier than x1 prime. Okay, there we go. Okay, so now putting this together, what do we have? Well, we've got x1 prime is equal to x2. That's the one that we got from over here. And then we also have, if I solve the second equation for x2 prime, then putting all the other junk on the other side, let's see, we've got 9t squared x1 minus 4e to the t x2 plus 7t. All right, so now we have a 2x2 system of equations. Okay, and things to note about this is that each of these is first order. Each contains only one derivative term, right? And so going back, that's part of this choice right here. If I choose this to be x2 instead of x1 prime, then there's only one derivative in that second equation, and it's this guy out in front, right? And then I guess the last thing is that looking at the system as a whole, that I've got an equation for each xi prime. Okay, so each xi prime appears once and only once, and it's the only derivative in the equation that it appears in. Okay, so now this means that we can write it in matrix form. So on the left side I have x1 prime, x2 prime as a matrix, and then I've got my equal sign, and then I've got a matrix with coefficients 0x1 and 1x2, and then 9 t squared x1s and minus 4 e to the t x2s. And then for the non-homogeneous part, I've got there's nothing in the first equation, but the other one's got a 7t in it. And so if you multiply out that matrix and do the vector addition, you'll see that we get exactly back to this one here, where I just treat this as a column vector, and this one here as a column vector. Okay, so now we've got this in matrix form, and so in general, this is going to look like x prime equals ax plus b. And so I use these, this is like blackboard bold or whatever this is. When I do like make the x sort of funny with the double lines there. And that's just supposed to indicate that we're looking at matrix functions. I do this just because it's hard to sort of separate the symbols, because what's going to happen is this. Over here, you notice we have that this guy, this is x2 is the second coordinate of this vector x, right? Later on, we're also going to be talking about multiple solutions to this equation, and they're going to be written like this, also with the subscript x1 and x2, and so I just don't want these to look the same, so I want these to be different. So in particular, these ones are scalar valued, and these ones over here are matrices. They're vector valued or matrix valued. Okay, so just a little note on terminology. Okay, and so now that we have everything set up in terms of matrices and vectors, of course, this means we can use eigenvectors. Before we look at general matrix systems, though, I just wanted to point out one thing, and that is that the types of matrix systems you get from converting an nth order differential equation are sort of specific. So let me show you with an example. So say we go to a higher order differential equation. Let's see, whatever, t squared y prime minus 6y equals e to the t, something like that. Okay, so let's do the same thing again. So here, so this is a new example. And let's see, so I'm going to take x1 to be y, x2 to be y prime, x3 to be y double prime, and then I'm going to have x1 prime is going to be y prime, and x2 prime is going to be y double prime, which is x3, and x3 prime will just be y triple prime. Okay, so this is going to be x3 prime minus 9t x3 plus t squared, and y prime I want x2. So again, I'm choosing the ones that don't have a derivative from the formula over here. And x1 equals e to the t. Okay, so when I go to write this in the vector formulation, I have x1 prime, x2 prime, x3 prime is equal to, and then I'm just going to be building stuff out of these equations that we have right here. So x1 prime is x2, and x2 prime is x3, and x3 prime is, oh, now we've got all sorts of stuff. So we've got an x1, and we've got a minus t squared x2, and we've got a 9t x3. Okay, so we've got that. And then there's our non-homogeneous forcing function guy. Okay. And so I just wanted to show that the type of matrix that you get from converting a system is always like this. So it's going to have zeros everywhere except for these ones in the off-diagonal positions coming down for the top part. And then there's going to be the bottom part, which will have all sorts of other stuff in it. But this is a very particular type situation, and in particular, these green zeros will always be zeros for something that's converted in this form. So in the sections to follow, we're going to look at more general matrix equations. So for an n by n system coming from an application, it may not have this specific form. So in particular, it's possible that these entries right here could be non-zero. And I should also say that if you have a system of two third-order equations, you can put the whole mess into one single matrix system. You're just going to have variables x1, x2, and x3 dealing with the first equation, and x4, x5, and x6 dealing with the second equation, and so on and so forth.